Fermions such as electrons interact, of course. For example, through their Coulomb repulsion. For such cases, we need two particle operators. Now, in the R or position form we've worked with before, we might have an operator, d, r, of two different coordinate sets for one particle and for the other. Then we postulate now that we could write the following, that we would replace our previous way of operating, which is our explicit operator here, with this new way, analogously to what we did for single particle fermion operators. And here we're going to look at what happens when we consider specifically two particle wave function operators. And these two particle wave function operators are simply this form here, with a 1 over root 2 because it's two particle. And later on we're going to presume we can generalize this to when we write down multiple particle wave function operators here with many more than two. But at least if we have two, we can write down this form and see how things work out. Well, substituting this two particle wave function operator into this expression here, we would have the following set of terms. So our annihilation operators from this two particle wave function operator and our creation operators from the adjoint over here, this two particle adjoint wave function operator, would give us this set that we would take out of the integral. We're summing over all of these possibilities here as we have to because of the wave function operator forms here, and we have this integral to look at and evaluate in the end. Again, we have a 1 over 2 here because we had a 1 over root 2 in each of these. Or equivalently, we could write it in this form. This is the same thing here, with this integral being this number in here. So if we were talking about specific single particle states A, B, C, and D, then we would be performing this integral for those specific single particle states to work out this number. And we're going to have to do that for all of the possibilities of the choices of A and B and C and D because we're going to sum over all of those to get the final result here. As I said, this is our formula for d, A, B, C, D here, this integral. Note that in this operator we've just written down here, that the order of the suffixes on the chain of operators is not A, B, C, D. The ordering is in the opposite sense for the annihilation operators. This different ordering emerges from the wave function operators and from the properties of Hermitian conjugation. We presume that the two-particle fermion operator that we've just written down here, by evaluating specifically for two particles, would remain unchanged as we change the system to have more than two fermions in it. We're not going to run through that algebra. We ran through it for the single particle case, and it was fairly complicated. So here we're just going to presume that that would work. And that argument, as I said, would be similar to our single particle one. So we presume that this here is a general statement, even if we go to multiple particles. We presume we could construct an argument similar to that rather complicated one we put together for the single particle fermion operator case. For two electrons of the same spin with Coulomb repulsion here, the Hamiltonian in the R form is, as we've written before, something like this. Here's our Coulomb repulsion term, two electrons, each of charge minus E. The repulsion term gives us a positive sign in here. Here's our kinetic energy terms for each of those two electrons. Hence, our two-particle operator formalism would give us this presumed form for this Hamiltonian. So that's just using the form we presumed from our previous argument. And this number here, in each case, is defined analogously to how we considered this number here. So we just put in the h in here, this one, and work out all of these numbers if we know all of these basis states we want to work with. Suppose specifically we have the 2 fermion state where one electron is in this basis state and the other is in this basis state. So in that case, the 2 particle state could be written in this form. We could start with the empty state, add a particle in state M, add a particle in state K. We evaluate the expectation value of the energy using this Hamiltonian for this state. That is, we're going to evaluate this form here, which becomes everything you see here on the right. So here's the BK dagger BM operating on the empty state over here. And we're going to get the Hermitian adjoint of that on the left-hand side. And here's our 4 operators from the Hamiltonian. Now, this looks a little frightening, but actually it's quite straightforward to work with that. So, if we look at this specific object we have to evaluate here, if you follow the rule of using the anti-commutation relations in this case to push the annihilation operators to the right everywhere you can, and you keep doing that, then you can take this string of operators here between these 2 empty states, and if you evaluate it that way, you will end up with this string here, these groups of 4 Kronecker deltas in this form. And we'll leave that as an exercise for you. It's quite straightforward. Hence, we have for the energy expectation value then, plugging this back in, this energy expectation value, which we'd previously written like this, we can now simplify down to all of this here because of these Kronecker deltas going into this summation here. So we're left with only 4 terms out of all the possibilities we might have had here. Now, in this expression we've just written down here, explicitly we have, for example, for this term here, and also it's the same as this one, this integral we'd have to work out. And for these other 2 terms here, we obtain this integral. We note this complex conjugate relation between these 2. So one of them, this one here, would give us this, and the other one would be the complex conjugate of this. Now, these are exactly the same terms as we previously calculated, using the R formalism to look at exchange. Remember, in this expression here, this particular one of these terms is the same as the sum of these 2 with the half in front of it. That's the sum of the kinetic energy for the 2 particles and the Coulomb potential energy for 2 electrons. So it is the energy we would calculate if the particles were not identical. These other 2 terms in here are the exchange energy. Hence, this approach we're doing here with this new operator form using annihilation and creation operators exactly reproduces the results we got when we did this the long way in the previous R formalism, where we had to explicitly symmetrize and antisymmetrize the wave functions appropriately with respect to exchange. Now we can see explicitly a point we made earlier. In this annihilation and creation operator formalism, we never have to explicitly introduce the antisymmetry of the wave function with respect to exchange for 2 identical fermions. It's there underneath, of course, but the operators are taking care of that for us. We see we have correctly acquired the exchange energy terms here. These have appeared naturally through the use of the anti-commutation relations for the fermion operators. Again, to emphasize this point, we see that quite generally boson and fermion annihilation and creation operators automatically take care of the symmetrization or anti-symmetrization with respect to exchange and automatically handle multiple particles. The way we write down the operators remains the same, independent of the number of particles in the system. This is therefore a very convenient and useful approach, and it's a very widely used and elegant notation.